middle of the screen, it's fine. So I'm going to be just taking notes in the middle of the screen, I guess. All right. So we're going to talk about variational formulations. I'm just going to write a few notes here. All right, so classically, variational formulation refers to constructing a functional or a variational principle that is equivalent to the governing equation. And we've already seen one of these because anytime you use Hamilton's principle, you develop a variational principle. So when we use Hamilton's principle, if you remember, basically when we compute those variations, sometimes we end up with variations that are like, you have like the derivative of a variation, right? The derivative of del u, right? And what we did was we used integration by parts to get those derivatives off of the variations so that ultimately we could invoke the fundamental limit of the calculus of variations and recover the governing equation. But had we not done that, had we just left the del u's in there, that would be a variational principle, okay? So Hamilton's principle is a very useful way to develop variational principles because you just sort of get them automatically. However, it's not always, if you remember when we used Hamilton's principle, we wrote down like a statement of, it's really just a statement of conservation of energy, right? T minus U, right? So kinetic minus the potential energy. That's a statement of conservation of energy, right? So we wrote down a statement of conservation of energy, or you might say that we started with an energy functional. Okay, it's not always possible to start with an energy functional. Like you might have a valid differential equation that you can't write an energy functional for. Right. The nice thing about variational formulations, or ultimately where we're going, the finite element method, is that you can use it to solve any partial differential equation. Or any differential equation, any boundary value problem, even if you don't start with an energy principle or an energy statement. So what we're going to do and work towards, we're going to go the other way. We're going to start with a governing an equation, and we're going to develop a variational principle for it, right? And so the modern use Sorry, like I said, my pen is not tracking well. Dang. So the modern use refers to a formula Sorry, that's supposed to, I'm not going to mess with the eraser because it's not working right now, so I'm just going to cross it out. Those of you that came in late, I mentioned to the class earlier, I forgot my laptop this morning, and so I had to borrow my son's because I had it, but for some reason the pen is not tracking perfectly, so I'm doing my best here. It seemed to work better when it wasn't folded backwards, so I may try like this. Okay. So that's basically what I just said. The modern use refers to a formulation where the governing equations are translated into equivalent weighted integral statements. So basically what we're going to do here is we're going to be given an ODE or PDE, and we're going to translate it into a weighted integral statement that will ultimately see as a variational formulation. Okay? So talk about weighted integral statement. All right, so you might remember from my lecture last time, the kind of philosophical or high-level lecture on finite elements. At the end, I said that what we're going to do in finite elements is we're going to try to find a solution U that's approximated by U of H, where U of H is equal to the sum from J to 1 to N, Nj, Uj, plus the sum from J to M, 1 to M, phi j, Cj. Okay, so remember I said that the Uj are nodes, remember? I said these are nodes. But right now, I haven't talked about any kind of discretization technique. So we have no nodes. So that leaves us, since we're not going to discretize anything yet, we're going to have U is approximated by U of H, which is equal to simply the sum from J from 1 to M, Cj, phi j, plus phi 0. And the sole purpose of phi 0 is to satisfy the boundary conditions. And I don't mean to imply that this is any different than that up there, because I could have said that J goes from 0 to M, so that, and then C0 would be 1, and so then we just have phi 0. But I wrote it this way just to point out that this guy is going to satisfy our boundary conditions. So for the next couple of days, we're going to work with a generic ODE And it's going to look like this. ddx So this is the ODE. It's going to be defined on the domain from x equals 0 to L. And then we're going to have the boundary condition that at u of 0, we have u0. And on the other side, on the right side, we'll have ax partial u partial x evaluated at x equal to L. So those are the boundary conditions. This is equal to Q0. Okay? And the reason we're going to work with this kind of generic ODE is because you should be able to see that we can solve lots of problems with this ODE, right? So for example, if A of x is equal to AE and C of x is equal to 0, we have our bar problem that I derived last time, right? Exactly. If A of x is equal to a tensor, well, I guess this is one dimension. So if A of x is equal to K over mu, permeability over viscosity, and you just change U to P, then you have a single steady state diffusivity problem, right? So you can solve, this is a generic equation, but if we can learn how to solve this by just choosing different values of the functions A, C, etc., then we can solve lots of problems with it. Okay? So for the problem we're going to consider right now, we're going to let L equal to 1. So we'll solve the problem on the domain 0 to 1. We'll let U0 equal to 1. We'll let Q0 equal to 0. A of x will just be x. C of x will be 1. And F of x will be 0. Okay. Now, without stating why, let's choose our approximating functions. So phi 0 is equal to 1. Phi 1 is going to be equal to x squared minus 2x. Phi 2 is going to be equal to x cubed minus 3x. And again, I'm not going to say why right now, but we'll come back to that later. Okay? So those are our phis in this approximation right here. Okay? So we have then, our equation is like that, and then we'll go ahead and distribute the derivative term. So we have du dx plus x d squared u dx squared plus u equal to 0. U of 0 is equal to 1. X du dx evaluated at x equal to L is equal to 0. All right, so this is our equation we're solving now. And now we're going to plug in our approximating functions that we chose somewhat randomly so we have U as U of H is equal to C1 x squared minus 2x plus C2 x cubed minus 3x plus 1. And we can see right now, remember this last plus 1, this is the thing that must satisfy the boundary condition. So at U of 0, right, so if I plug in x equals 0, then this equation just equals 1. And so we do satisfy the boundary condition.
Why the minus disappear?
What's that?
The minus. We have a minus.
The minus? Oh, I see. Yeah, so that should be still there. Ah, gosh. That's how far off the should be here. So those should be minus, right? Okay. All right, let's go ahead and compute the derivatives. So I'm basically just using this approximation of U, and I'm going to compute du dx, okay? Just the terms we're going to stick them all back into the differential equation. We're just going to compute the terms one at a time. So du dx is equal to and d squared, the second derivative of u with respect to x is then okay, so then if we stick those back into the equation, then we have that guy. Now, is that equal to 0? Well, depends if we could choose the C1 and C2 such that it equals to 0, right? And so the only way that could be true is if we gather all this, basically if all the coefficients of the powers of x are equal to 0. So if we gather up the coefficients of the powers of x, we end up with so we can simplify that to be minus 9 C2 plus C1 equal to 0. That simplifies to minus 6 C1 minus 3 C2 equal to 0. Okay. So, turns out there's no C1 and C2 that satisfy all those. And why should there be? We had one equation and we had two unknowns, right? So that's why we can't solve it. So let's see what else we can do. All right, let's go back. To our original equation. So we had all right. Now, would everyone agree that as long as I, just like any rule with algebraic rule with equations, I can multiply that equation by something and I don't change the equation, right? As long as I multiply both sides, right? So I can multiply by 1, and I can divide it away, right? I can multiply by x, I can divide it away, right? So I don't change the equation if I multiply by something, okay? So let's multiply this equation on both sides by something arbitrary. We'll call it del u. So arbitrary function. And I haven't changed the equation. Next, again, I don't change the equation if I integrate over the body, right? So if I integrate from 0 to L dx, 0 to L dx, of course, this is just 0, right? The right-hand side is still 0 because the integrand is 0. So what we have here, you can look at this like this is a residual, and this is a weight. So you could write it like so our residual with plugging in, so we're going to plug in the approximating functions into our residual and write down what it is, right? We already wrote that down, but let's write it down again here. So C2 x cubed, now the terms have been gathered using what we did right above. And so let's choose our weights. And we're going to choose the same amount of weights as there are unknowns in our residual. Okay? And we have to, the only rule is that we choose them to be linear independent. Right? So choose del u1 equal to 1, del u2 equal to x. So they're linear independent, right? There's nothing I can add to 1 to get x.
Professor, why have you chosen 0 on the right hand side? Because it could be any constant, right? To differentiate any constant with respect to x.
Sorry, what? I don't understand. Where?
On the right hand side.
Why is the right hand side equal to 0?
Yeah.
Well, the equation was just
any constant, right? Like if you integrate the constant, it becomes, if you integrate 0, it should become a constant, right?
Well, I mean, the original equation was this equal to 0.
Yeah.
And then we just multiplied both sides by a function.
And then you integrate it.
And then you integrate it, right? Yeah.
So the right side should have a constant value. If you
No. I mean, the integrand of this is 0, right? So the integral of 0 is 0.
So normally it's constant, but there is
normally
limits
it's constant.
from L to 0, so you subtract.
The integral of 0 is 0,
Okay.
right?
I don't know if you get.
Well, the integral.
So
open
you
integral
normally
is
the integral is
constant,
constant, but there is boundary condition. So it's like the
Oh, yeah,
constant
yeah.
minus the
Yeah.
constant. which is
Yeah.
zero.
All right, so now I've chosen two weights, and I'm just going to plug those into our equation, right? So I'm going to write it 0 equals the integral from 0 to 1. The first weight is 1 times the residual r. I'm not going to rewrite it here. Okay? And now I'm going to go ahead and perform the integration, right? So I'm going to basically just, in this case, just integrate from 0 to 1 the residual. Okay? And I'm just going to write the answer down. So that's one equation. And now we have another equation using the second weight, which we said was x times the residual, and then carry out the integration. Now we have two equations, two linear equations. We have two unknowns. So we can solve that for C1. And if we do, it's equal to 222 over 23. And C2 is equal to minus 100 over 23. So if we take those two coefficients and plug it back into this approximation term here, right? So if you plug in C1 and C2, then this is an approximation to the solution, to the real solution U. Right? Now we'll see later like how good of an approximation it is, but it's an approximation. We'll work an example. I don't think we'll get to it today, but next class we'll work an example like in the computer, where we on a problem where we have an analytic solution and we'll compare this method to the analytic solution. We'll see how well it does, okay?